Perfect timing for a severe stay-at-home alert on my phone. Sorry. Um, anyway, all attendees are muted, but we wanted to let you know that there is a Q&A button at the bottom of your screen where you can type in your questions throughout the webinar. Go ahead and type them in, and we'll take questions at a couple points throughout the webinar this afternoon. If we can go to the next slide, hopefully. But I did want to let folks know, like I mentioned, this is the last in our buildings webinar for this year, but we have a bunch of sustainability webinars from earlier this summer. We have 3 buildings webinars that have already taken place, and there's recordings and presentations for those, as well as 8 or 9 previous webinars that took place this summer on a variety of topics, including electric vehicles, food waste, water conservation, recycling, and biking, among other topics. So those are all can be all found at that link that you see there. This webinar will be recorded and placed on that same website by the end of the week. And I wanted to let folks know we have one final webinar on a different topic, sustainable holidays. And that will be on Thursday, December 17th at 4 p.m., where you can learn how to make your holiday decor and home more energy efficient, comfortable, and safe. And we'll also provide waste reduction tips for the holidays. And you can learn how to properly dispose of holiday-related items like wrapping paper, use turkey frying oil, Christmas trees, use batteries, packaging, and food containers. Again, that can be same link that you see on the slide right here. Again, that's next week on December 17th at 4 p.m. And we hope you can join us for that. And now I'm going to pass it over to Lynn Mitschke, who will kick off our webinar this afternoon. Take it away, Lynn.
Okay. Hello, everybody. Welcome to our last webinar in our part of the series. And we have a lot of information about a very relevant topic at this point. So we'll start with Kalina Ferraro, and go ahead, Kalina.
Thanks, Lynn, and thanks to the City of Chula Vista for organizing this. My name is Kalina Ferrero. I'm a mechanical engineer and principal leading the San Diego office for Integral Group. Integral Group is a deep green engineering firm, so we specialize in high performance buildings and sustainable design and doing the heating, cooling, ventilation, plumbing, electrical, sort of all the systems engineering for that. So today we're going to talk about ventilation, which falls squarely within that suite of services. Specifically, we're going to talk mostly about non-residential, and I know Rich is going to speak right after me, addressing more on the residential side. So if you can go to the next slide, we'll jump right in. So just to get started, kind of an overview, what is ventilation? When we say ventilation, what specifically are we talking about? If you look at that cutaway cartoon I have of buildings, there's lots of different airstreams moving around the building, doing lots of different things. Some things are doing heating and cooling, some are maintaining pressurization. When we talk about ventilation, we're specifically talking about the air that goes into and out of the building. So it's the fresh outside air coming into the building, and then either contaminated or, quote, used exhaust air that's leaving a building. So those are the two airstreams that we're talking about when we talk about ventilation. And then just for those that aren't familiar with some of these terms and the acronyms that we'll be using, the way we describe airflow in spaces is either as a cubic foot per minute, so that's the flow rate, and I have a little cartoon there that shows that little cubic block of air. If you want to think of a cubic foot per minute, it's one sort of cubic foot moving through that room at a rate of 1 minute. The other way we describe airflow in rooms is how long it takes for all of the air in that room to get completely changed out. So that air getting changed out is an air change. And we can talk about how many times that happens in 1 hour. So 1 air change per hour means that the entire space of that room is completely replaced in that hour. So those are the two metrics that we use to describe airflow in spaces. Next slide, please. So big picture, why ventilate? And if you notice that picture, those were back in the better days when we could sit there and be next to people and collaborate. And ultimately, why we ventilate is really for human health. So when we think of the fresh air coming in, that's to bring in fresh oxygen and dilute the CO2 that people breathe out. So that maintains alertness and productivity. It's also for moisture and humidity control. So if you don't have enough ventilation, that's where you tend to accumulate humidity and you can get mold issues. On the exhaust side, we do that for odor and control and containment removal. So this could be in kitchens so that we don't, it could be something as simple as making sure that the break room sort of fish microwave smell doesn't spread throughout the office, or it could be something much more important like lab exhaust to make sure that dangerous chemicals are being kept away from people. And then the last one is pressurization. So again, in some spaces, so healthcare applications or clean room applications, we sometimes need to maintain one area positive relative to the others so that we can keep that space very, very clean. And then just for general comfort purposes, we generally keep buildings a bit more pressurized so that we don't get leaky drafts leaking into the building. So all of these reasons, really it's for the occupants, right? We ventilate buildings that are going to be occupied. We ventilate occupied spaces. Next slide, please. So how much do we need to ventilate? There's a minimum requirement established in the building code. So obviously the building code has all these multiple parts and there's requirements in all of them. The primary ones that dictate the minimum code levels for ventilation are the California Mechanical Code and the California Energy Code. They have similar requirements, but they're slightly different. So we do need to check both. And then in addition to that, in some specific cases, so labs, healthcare, clean rooms, some other applications, there'll be additional standards that we'll have to design to meet. And then there's some voluntary standards. So people talk about high performance buildings, or maybe they want to achieve LEED certification or well building certification. So those are voluntary standards that may have additional ventilation requirements. So there's lots of different sources that we need to look to figure out how much ventilation to provide. And just to give kind of an example of what that looks like, if you can go to the next slide, I've pulled just some screenshots of what these code requirements look like. And it's really dry, and obviously these are small tables, so I think the details are less important. But what's important to take away is that for every different type of occupancy, so if you're in an office versus if you're in an auditorium or in a classroom, they all have different requirements. And the requirements are determined based on the number of occupants you expect to be there. So there's a certain amount of CFM per person and the total area of the space. So there's a CFM per square foot requirement. So we have to look at both of those. So like we said, ventilation is for people. So we look at the number of occupants there and we look at the areas that are going to be occupied spaces. And between the two of those will dictate our minimums. And then some of those other standards might increase above that minimum, but we can never be below that code level. Next slide, please. So that code level and those standards usually dictate systems that we would put into most buildings. And those are very conventional type of systems. And I have a couple of slides coming up to sort of describe what that normal conventional system looks like. But I think it's important just to generally be aware that the conventional systems don't necessarily mean the best types of systems. So when we talk about code requirements, those are really the minimums. And these high performance buildings actually, they perform much better on a number of different metrics. So carbon dioxide levels are generally lower in green or high performance buildings. That leads to improved productivity and alertness. Ventilation rates are much higher, and that's how you get those lower carbon dioxide levels. And both through the selection of materials, but also because of that higher ventilation, we can have much lower VOC levels. So VOCs are those organic compounds that come off of carpets or paints or new plastics. And really flushing that air through the building, bringing in the outside air and exhausting. That's really how we dilute and remove those VOCs. So you can see these high performance buildings do perform better on a number of those metrics. But most of the buildings that we have still sort of fall into this conventional category, and those are pretty typical ranges for conventional buildings. So let's look a little bit at what those systems are, just to get an understanding for them. Next slide, please. So most commercial buildings, so these non-residential buildings, generally have a centralized air handling unit. So you'll see these as packaged units on the roof, or sometimes they're air handling units inside the building. And those pull in outside air in the unit and they mix it with return air coming back from the building. So it's a mixed supply air system that goes down that does both the ventilation, which is the outside air, but also the cooling. So we're blowing a lot more air into that building because the air is doing two jobs. And then we have another set of ductwork that collects all that air in the building and brings it back up to the unit. Now, some of it might get exhausted separately through things like bathrooms, or we talked about hoods. Some of it comes back up to the unit, and there's dampers up there that will bypass some of it back to the return stream, and some of it just gets let out as just extra air. So that's just relieved. But they're combined sort of mixed air ducts in both cases. So that's what it looks like sort of at the roof at the system level. If we break that down to the floor level, next slide, please. What that looks like at the floor level is that we may have multiple tenants. So in this example, we've got 5 different tenants that would all be served off of that same unit. So when we talk about these mixed streams, it's that same unit that's supplying this mixed air to all 5 of those. Now there's dampers to break that down, and it gets broken down even further at the zone level. And so if you go to the next slide, we can see a little bit what happens at the zone level. So at each of those zone levels, we have terminal units. Now, in most buildings, those are VAV boxes. So that's just a damper that opens and closes depending on how much cooling you need usually. Sometimes that's fan coil units, which will have a little coil to provide extra heating or cooling there. So there's a few different options for what those terminal units are, but usually it's just a portion that controls the temperature for that specific space and has a branch that comes off of those main ducts at the floor. Next slide, please. So at the room level, what we see is that terminal box is, you can see sort of that diagram that shows the ductwork. That terminal box would be the VAV. That's going to have a damper that opens and closes, and depending on how open or closed, that blows the supply air into the room through a diffuser in the ceiling. And we're all used to seeing those square diffusers in the ceiling. Now, our conventional systems are a mixed air system. So not only are we supplying a blend of cooling air and outside air, when it gets into the room, what it does is it curves along the ceiling and creates great big circular patterns in the room that keeps the whole room a nice, even, comfortable temperature and mixes and dilutes any of those contaminants that are in the room. Now, in these conventional systems, we might be supplying somewhere between 0.75 and 1.5 CFM per square foot. But like we said, that's a mixed supply. So only about 15 to 20% of that is usually fresh outside air in an office space. Which means that your ventilation airflow rate is much lower. It's 0.15 to 0.2 CFM per square foot in most just general conventional office spaces. And again, if we want to talk about air changes, we said an air change is how long it takes to change out all of the air in that room. In office space, 4 to 6 air changes per hour is pretty normal of that total mixed supply air. Now, some of that is just circulating through that system. So the total outside air that's getting replaced is really only about 1 air change per hour. So that's kind of the look at a conventional system. But like we said, it does circulate through that. And one of the other ways these systems help is not only are we bringing in ventilation air for dilution, we also have filters built into that system. So that helps with the contaminants as well. Next slide, please. So the filters, and people are talking a lot more about filters now in the age of COVID. So when we talk about filters, filters get measured by what's called a MERV rating, which is the minimum efficiency reporting value. So that says for all of these different size particles, what percentage of those particles are going to get captured by that filter. And these are all tested to specific standards. And the code requirements for these filters have actually improved in the most recent code cycle. So in the previous code cycle, a MERV 8 filter was the minimum requirement. And a lot of the high performance building standards, the LEED ratings, well building standards, they would require MERV 13. California has a pretty progressive building code. And so California made that higher performance a code requirement in the code that's in effect now. So everything as of January 1st. All ducted systems, the outside air and the return air, have to be filtered to that MERV 13 rating. And that's at a level, the MERV 13 rating is at a level that it's able to capture a lot of these droplets that people are talking about that have been in the news. So you can, if you sneeze, there's sort of that mist that comes out, that can be captured by a MERV 13 filter. So that is a pretty high performance filter that's now the code requirement. Next slide, please. So if ventilation's so good, why don't we do more of it? So what are some of the challenges with ventilation? So certainly there's energy use, right? We talked about how this gets done. We're blowing air around a building. So in order to move that air around, we're using fans. And those take a lot of fan power. We're also bringing in outside air that might be too hot or too cold, so we have to heat and cool that. So there is an energy penalty associated with more ventilation. Also, there's space, right? We looked at that system in the building and we had great big ducts coming down from the air handling unit. So those ducts, we need horizontal space in the ceiling, we need shaft space in the floor plate, we need somewhere to locate that equipment. So there's space required for it. And then there's cost, right? We've got to buy that equipment and the ductwork, and then as we're using that energy, you've got to pay for it as an operating cost. So those are sort of those are the primary reasons that people usually talk about. One of the other challenges with ventilation, which I think gets overlooked because it's harder to see, is really just the ventilation effectiveness. So I've got these two diagrams, which are a plan view looking down. I think this is actually a library. And so you've got a curved wall, and then there's a central core area where I think the elevators are. And we can see the airflow patterns there. And what those airflows are is the green is where we have nice, quickly moving air, and the brown is really slow air. And so we can see these stagnant pockets that really aren't getting supplied well. And this is pretty typical because when we look at that zone layout, what happens is the supply usually happens around the outside edge, and the return usually pulls back at the core. And so if you have some obstacles in the way, in this case, it might be bookshelves or whatever, the air is always going to take the easiest path. And so if you don't look at it very carefully, some of these dead spots, it's really hard to see. So there's modeling software called CFD that we can look at to evaluate the effectiveness here. And then there's also field testing. If you want to see how well your existing system works, there's smoke tests that you can actually kind of watch, these smoke machines move the air through the room. But ventilation effectiveness is something that's important and increasingly important as we're talking about ventilation in spaces with relation to COVID, because what you don't want to do is be sitting in one of those dead spots where there might be lots of air moving around you, but you're not getting any fresh air if you're in one of those brown zones. Next slide, please. So what are some of the ways that we can do ventilation better? So that picture we looked at before with that mixed air condition where we supply air up at the top and we mix it all together in the room to get good even dilution. An alternative to that is what's called displacement ventilation. So instead of supplying air up top and relying on the cool air sinking to mix it up, we supply air down low at the bottom of the floor. Because it's a little bit cooler, it tends to just creep along the floor. And then when it hits a nice warm body or a computer or something, that heat will make it lift up. And then we put our return up high to carry that away. So we get once through air that just passes in one direction, going up through the room and then out. So we end up getting much cleaner air because you only breathe it once. It's not mixing around, and we're able to displace a lot of those contaminants much more quickly. Next slide, please. Another option is a dedicated outside air system. So when we talked about a conventional system, we said it was a mixed air stream. We were doing our supply air for cooling, had both ventilation air and also return air that was recirculated. In a dedicated outside air system, it's 100% outside air coming in. So your air system is just doing the ventilation, and you'd have other things in the space that do your heating and cooling. So that might be chilled beams, that might be radiant panels. It could even be fan coil units that just recirculate. But this lets us supply the ventilation just directly where we want it and not have to be tied to meeting cooling loads at the same time. So it gives you more control and precision in the way your systems get laid out. Next slide, please. And then the last other ventilation strategy I wanted to talk about was natural ventilation. And this is really good here in San Diego because we have such mild conditions. We can use natural ventilation for most of our year. And you can do this with just manually operable windows, or you can automate those windows or do louvers. This provides both cooling and ventilation, and just the natural stack effect, if this gets laid out properly, can move that air for you. So you don't have to use fans. You can just let the heat pull it up towards some high level openings in your building. You can add fans to help move that around. So either ceiling fans or fans to boost that airflow. But one of the biggest things with natural ventilation is that in a well-designed natural ventilation system, because you have windows tend to be fairly large, because stack effect moves air quickly, you can get up to 20 to 25 air changes per hour. And if you compare that to what we looked at for a conventional system of 4 to 6, this is a lot more airflow. So you get much more fresh air, you get much quicker elimination of contaminants. So natural ventilation has a lot of benefits if it gets designed in properly. Next slide, please. So one topic we wanted to talk about quickly here, and I'm wrapping up, but we have been having a lot more conversations now as COVID is obviously transforming the way we do everything in our lives. We want to talk about how do we change ventilation systems to really respond to COVID. Next slide. And so the first caveat is that this is a process that everyone's still learning. So obviously scientists and medical professionals are still learning about COVID. We're not even at their level. We're trying to react to it on the engineering level. So as they understand how the virus works, we have to take that and interpret how we can design building systems to mitigate that risk. We obviously can't eliminate it, but there are some strategies that we can implement that really reduce that risk. Next slide, please. So what we know so far is that there's lots of different avenues that COVID transmits through. But the primary ones seem to be these ones in red, which are droplets going directly from an infected person through the air to another person. And that those droplets, if they hang around in the air, they can start to shrink. So some of the moisture in each of those droplets will evaporate and it essentially just becomes like the little particles inside. So the virus and maybe some dust get condensed into these smaller particles that are droplet nuclei, and those can still be contagious. So those two airstreams are really the ones that we're focused on when we're talking about adapting ventilation systems to mitigate for COVID. Next slide, please. And there's really three main strategies that we focus on if we're trying to adapt the system in response to COVID. So the first is to really maximize ventilation. So the more we can just move air through that space and then back out the building, the more we dilute any of those particulates that are there, the less particulate that's there, the less risk of contagion you have. So maximizing ventilation, increasing the outside air as much as you can. And then the second step is minimizing that recirculation. So if you can maximize the amount of air and then just move it through your space once, so either in that displacement strategy or in natural ventilation where we're just moving it through and then out the other window on the opposite side. But even in a ducted system, looking at your zoning to try to get your air to just pass through your space as little as possible and then out again. And to avoid circulating it between one zone and another. So some systems circulate between different rooms or even different tenants, and we really want to reduce that. And then lastly is to optimize the filtration. So like we said, some of these older units, if they were designed to previous codes, could only have MERV 8 filters in them. So checking those fans to see if you're able to upgrade that filtration to something like a MERV 13 or a MERV 14. MERV 13 can capture those droplets. Up to a MERV 14 can start capturing those nuclei particles. So improving the filters that you have either in existing units if the fans are capable of doing that, or potentially doing something in your room itself if you have a little recirculating filter system that can help pull any particles out of the air as well. Next slide, please. So ultimately, we do need to look at each building individually if we want to see what these options are, right? There's limits in existing systems to what you can do. So when we've been called to audit existing buildings and see how we can improve them, the first things we do are to look at the sequences of operation. So is there a way that we can do a night flush so that we flush the building out before people get there and after people leave for the day? And can we update those control sequences to really boost that ventilation or change the zoning to minimize that recirculation? And checking the systems to see if they can accommodate higher filters. In new buildings, we try to incorporate some of these alternative strategies that we talked about and do more modeling to make sure that we get effective ventilation in the spaces that we have going through them. Next slide, please. I think that wraps it up for me. So the only question I see there is whether slides will be available. I'm certainly happy to have them be distributed. I don't know if Lynn and Barbara can send those out directly. But so I can let them respond.
Kalina, I will send it out after the webinar.
Perfect. Any other questions at this time?
Thanks, Kalina. There was the one question that came in to ask, have you worked on projects to upgrade the ventilation system of a building this year due to the COVID-19? And if yes, can you tell us a little bit about it?
Yeah, sure. So the way we've seen COVID impact our ventilation kind of comes in two different flavors. The first is for the existing buildings, and the second is for the ones that we have in design right now. So for existing buildings where we've been called to do what we call it essentially doing a COVID audit. So we'll go out and we'll look at the systems. There, we're trying to do as much as we can with the systems they have. So first, it's making sure that the systems are functioning correctly. Outside air dampers tend to be one of the first things to fail just because they get rusty and things like that. So making sure that your outside air damper is working, and then checking the system to see if we can increase that outside air amount as much as we can. So sometimes it's set to code minimum, but you have capacity to run it much higher. And so evaluating that and adjusting the sequence to improve that. Improving filtration is another one that we do pretty regularly because usually there's extra fan power, but again, that has to be checked. So we haven't been specifically asked to say like do a full new system replacement due to COVID. I think the strategy that most existing buildings are taking is that, you know, during COVID, during this worst part of the pandemic, people are being sent home anyway. So what they want to do is kind of do as well as they can with the systems they have, but we haven't seen wholesale changes to existing systems. In new designs, it's a bit more of a range. So in some cases, we have been asked to do a wholesale redesign. So maybe it was a conventional system that we were designing initially, and it's now been changed to a displacement system with Radiant. That's a pretty common one that we're doing now more of. And in some cases, they still want a more conventional system, but we might provide more dedicated exhaust to common spaces. So for example, lobbies or conference rooms, rather than having that air go back as part of the mixed return stream, we exhaust that air directly. And so I think treating specific spaces very carefully, especially where you have a high concentration of people, just changes the way we think of that. The other thing we start thinking of more is how air moves through a space. So if we're supplying air at one side of the room and pulling the return air from the opposite side of the room, if this is a great big open plan office, we have to think about the fact that we're dragging that air across all of those people. So you get the people near the supply that get fresh, we call it first air, and the person at the end of the room is getting air that's passed over all of those people. So what we might do instead is add more points so that we supply more places along the room and we return more places along the room so that we don't drag air over as many people. So that would be another example of some of the ways we change our design. I see another question in the chat. How big would the energy use impacts be of some of these types of changes if they could be offset with energy efficiency or solar? So in San Diego, we have pretty mild conditions, so we don't see a huge energy impact from increasing ventilation within reason. I mean, obviously, on our peak days, you do have to be careful, but we operate in what's called economizer mode quite a bit of the time anyway, which is using sort of that free outside air for cooling. But there is still energy impacts. It's a tough question to sort of ask in a short or answer in a short way because it's specific to the building type. But there are ways, like energy recovery is a way that we can reduce the impact, so we can recover some of that heat that's lost in the airstream and put it into the incoming air. That's one way that we can mitigate the efficiency if we go to a higher ventilation type system.
Okay, whoa, that's lots of information. So now we're going to move along to next slide, please. And welcome back, Rich Williams, and we're going to jump into the residential side. Rich.
Hi, everybody. This is Rich Williams. I'm the VP of Alliance Green Builders. We're a general contracting firm in North County, San Diego. In our presentation, we'll primarily be discussing what's in the California Code for low-rise residential ventilation and what we do as a builder to address that code. Next slide, please. So we are now under the 2019 Energy Code as of January 1st of this year. Section 4.6 of the Energy Code Standards addresses indoor air quality and mechanical ventilation. This part of the code requires that we have mechanical ventilation that provides outdoor air into residential structures. And it is important to note that the ventilation must be continuously operating all the time. The amount of air we are required to provide into the structure is dictated by subsection 150.0, and that section refers to the formula in ASHRAE Standard 62.2 2016. So what is that formula? Next slide, please. The American Society of Heating, Refrigeration, and Air Conditioning Engineers are the ones we blame for how much air we have to bring into a dwelling unit. Their 2016 total amount of airflow in cubic feet per minute is calculated at 3% of the floor area plus 7.5 times the number of bedrooms plus 1. It's not a complicated formula. It looks at first glance here. It's essentially, let's take an example here of 3,000 square foot home with 3 bedrooms. So it's 3% of 3,000, which is 90, plus 7.5 times 4. That turns into 120 cubic feet per minute of total ventilation airflow that's required for ventilation into that residence. We do get a single family infiltration credit that ASHRAE allows, but nobody ever takes that credit, and nor is it actually utilized in the Title 24 modeling. So we just ignore that credit, and it's hard to determine anyway. Next slide. There's no need to fear your CF1RAs here. You don't have to worry about that formula because in your Title 24 report, you'll notice down here where the orange arrow is, it actually tells you what the continuous ventilation requirement is. This is a project that we're bidding on right now, and this requires a total of 100 CFM for this residence. Next slide, please. So ASHRAE allows for 3 different ways that we can provide continuous ventilation: exhaust only, supply only, and balanced ventilation. Exhaust only is just exhausting air from within the structure, and supply only is pushing air into the structure. Typically, we only do exhaust only because it's simple to do. That's why supply only is crossed out there. And the typical approach that builders utilize is to put 2-speed bath fans for exhaust only ventilation. So these actually, I'll get into the next slides to show you a little bit about this, but you're exhausting from the structure and then pulling makeup air for those fans through the building envelope, but also you can put in passive inlets to provide air instead of pulling it through the envelope, and I'll show you a couple of those passive inlets in upcoming slides. Or we can do balanced ventilation utilizing heat recovery ventilators or energy recovery ventilators. And the nice thing about those is they do add a little bit more cost versus 2-speed bath fans, but you actually can get rid of those bath fans and the laundry fan with a balanced ventilation system. Next slide, please. So for exhaust only ventilation, I decided just to go ahead and take a couple of pictures of the fan in my own house to show you folks how this works. On the slide on the left, you'll actually notice something I'll point out a little bit later. The grills are a little bit dirty there. That's going to be something I'll bring up in a slide a little later on. On the right-hand side, it's opening up the cover, shows the guts of the fan on the inside, and you can notice that I've got a little bit of house wrap around there, so I'm not pulling air from the attic space. Next slide, please. So on the left, you'll see these 2 arrows here. Those are pointing to the settings for this fan. On the right-hand side is a close-up of those settings. And these 2-speed bath fans, they're very sophisticated. They're fantastic fans. If you look up to arrow number 1 there, it shows that for my home, I have model number 0511 that's shown by the yellow arrow there. And I have it at 30 CFM. There's 2 models that you can get here that have different settings. That's why you have a display that shows those different types of settings depending upon your model. So in my house, it's I only need it's only 750 square foot, so 30 CFM is sufficient for me. So that fan is operating continuously, exhausting 30 CFM of air out of the house. Down at arrow number 2 down there, you see I can actually turn the fan on at the wall if I'm showering or whatever, I can take it up to the second speed, which is at 80 CFM. It does actually operate automatically too. In arrow number 4, you can see I have it set. Once if I'm showering, the relative humidity goes above 80, it'll actually go on its own up to that 80 CFM fan speed. So that's a really nice feature. I actually never turn the fan on in the bathroom. It just automatically goes on. And then if you look at arrow number 3 up there, it's set at 10 minutes. So what that means is that after I turn the fan off with the switch, it'll actually stay on at high speed for an additional 10 minutes. Or if the relative humidity drops below 80%, it'll stay on for an additional 10 minutes as well. So these are very sophisticated bath fans. They're a nice, simple way for builders to be able to achieve their CFM airflow as required for IAQ on your CF1R. Next slide, please. So exhaust-only ventilation with 2-speed bath fans. As I said, they're an expensive strategy to meet code. If you had 90 CFM requirement, for example, you could put 3 different fans in there in the home. They generally work pretty well. It's better than having no ventilation at all in a structure. The problem is that they are noisy, especially in a tight, energy-efficient home. They will ramp up to the speed required in order to provide the airflow. So if those fans are starving for air, you've got your doors and windows closed, and you're laying in bed at night, you actually can hear those fans. So that's not particularly a great feature to have. Say in your master bathroom, but no fun sitting in bed listening to a fan running. As I showed you in that earlier slide, the grills can get dirty because they're continuously exhausting air from in the house. Also, you're sucking fresh air through the building envelope. So this is what we call uncontrolled infiltration. Joe's got a great slide in his presentation that will show you why fresh air through the envelope is not a great idea. That's not where you want to get your fresh air. It doesn't provide indoor air quality nearly as well as a balanced ventilation system does, and we'll get into a balanced ventilation system next. Next slide, please. Oh, well, better than pulling it through the envelope is you can actually put in passive inlets that allow air to flow freely into the structure. So these are examples of systems that we use. They are better than pulling it through the envelope, but the problem is that they only allow 18 CFM of airflow. So you need to have several locations, and you've got unconditioned air being dumped into the house. Where are you actually going to dump that unconditioned air such that you're not going to end up with kind of uncomfortable conditions in there? They do have filters in them, but the problem is those filters get dirty pretty quick, and they do need to have constant maintenance as well. So it's it's better than infiltration through the envelope, but it's still not optimum. Next slide, please. So this is an example of a passive inlet that we put into a home under construction for us right now. This happens to be the pool house, just a small space. It does have a 2-speed bath fan in the bathroom, so it's constantly pulling air into the structure. And then, as you can see on the middle slide there, that's the little square on the wall right there. That's the inlet, the inside portion of the inlet. And on the far right-hand side, that's the outside portion of the inlet that's pulling air into the structure. Next slide, please. So that was then, this is now. California is trying to move us away from exhaust-only ventilation we've been using for quite some time now towards a balanced ventilation system using heat recovery ventilators and energy recovery ventilators. In Canada, it's code throughout all of Canada that you actually have to have HRVs or ERVs. Actually, I think it's just ERVs up there. So they're also encouraging us to build tighter building envelopes. How they're doing that is in the current code as of January 1st of this year, the Title 24 energy modeling is providing significant credits for incorporating HRVs and ERVs into our projects, and to also make buildings more airtight. Now, the really great thing about what they've done in the new modeling is if you include both the ballast ventilation system and you make a building more airtight, you get what we call a super bump in the credits. So the sum of both those credits is actually, and combining them, is much greater than just the individual credits added together. So now that QII, quality installation is just assumed you're going to be doing that, energy engineers are going to be looking for what they can do to get buildings into compliance if they're trying to achieve Title 24 compliance. And this is a great tool to have in their bag of tricks for doing that. So we'll probably be seeing a lot more ERVs and HRVs specified for residential construction. So that's going to be in the years to come, and probably one of these code cycles will actually see them mandated for all of our homes. Next slide, please. So let's talk about HRVs and ERVs. They really are the optimum ventilation strategy for indoor air quality. So what we do, you can see in this particular slide, this happens to be an HRV or ERV up in an attic space there. On the left-hand side, you can see that we're exhausting from a bathroom and a kitchen. That's the red is going out, and then we're bringing fresh air into the living spaces where we really want to have fresh air in our bedrooms and other living spaces. Next slide, please. So HRVs and ERVs, what are they? So a heat recovery ventilator is a system which recovers the sensible heat that's coming, that you're exhausting out of a building, and does an exchange with the unconditioned air that's coming from the outside of the building, or supply air. An energy recovery ventilator does sensible heat, but also recovers latent heat exchange as well. So think the humidity of the air. I'm not going to get, it's probably another hour conversation discussing the differences between sensible and latent heat. If you don't know about that, you can go ahead and research that. HRVs and ERVs can be dedicated standalone systems, or they can be incorporated into forced air systems. Next slide, please. So this is an example of an HRV incorporated into a forced air system. The bottom right-hand photo I shot at Production Builder out in Prescott, Arizona. Mandalay Homes, they're arguably the most progressive production builder in the country. That's to give you a better display up on the right-hand top right there. You can kind of see this HRV unit that's in between in the bay there, in the truss assembly right there. In the bottom left, it shows you kind of how this works in your existing forced air system there. So on the far left, you can see we're drawing air from the outside to the inside, and then the black ducting there shows the exhaust air. So that's going through this HRV unit. You can see where the diamond-shaped figure is right there. That's the core that actually does the heat exchange between the conditioned exhausted air from the building with the unconditioned air that's coming into the building. You can see that the exhausted air is coming from the air return at the top, and then the supply air is going back into the FAU and the far right there. So that's a fairly inexpensive way to bring balanced ventilation into our homes. It's not perfect. Next slide, please. So the pros of that is it is a relatively inexpensive and it's pretty quick to install. That system Mandalay puts in for about $1,000, self-performing themselves in the installation. The problem is it does use the returns for the exhaust, and therefore it's not as controlled as a dedicated standalone system, which exhausts only from the wet areas and then supplies only to the living areas. Also, it's really not as balanced as a dedicated system. Exhausting air in appropriate quantities from the areas we want to exhaust, and then bringing appropriate quantities of fresh air into the living spaces based upon the living spaces sizes to make it appropriate. Next slide, please. Oh, I think we went back. Okay, next one. There we go. Okay, this is what we typically try to put into our homes here, a dedicated standalone ERV. That system on the far left is a passive house project that we built out in Ramona. Going back to that slide you've seen before, again, we are exhausting from those wet areas, which are kitchens, bathrooms, and laundry, and then bringing in some fresh supply air into our living spaces, which are bedrooms, and other living spaces. Next slide, please. On the far left, it's a little bit more of a messy system that's in a home we're under construction on now. This is one of two systems in that home. It looks a little bit messier in this photograph than it really needs to, because we've got somebody, as I said, it's under construction right now, that's using our equipment there as a workspace and putting his supplies and tools over there. Inside the home, at the top there, you can see this is one of the supply ports here. So you can see those tubes that are on the left-hand slide. They're going up into these supply ports right here. It has two tubes going there, bringing fresh air in. And on the bottom right, that's the finish fixture right there. And that little disc at the bottom screws in and out. So we can actually adjust the amount of airflow. So when we commission this system, we know exactly how much airflow we need to exhaust and bring into each airspace. So it's fully commissioned so that we have the appropriate amount of airflow into each space right there. Next slide, please. So as an alternative to that other system you saw on the previous slide there, we do have these low-cost paired HRV systems. Two projects we've installed those in are the home at the top here and the home at the bottom. Now, each of these paired systems brings in 15 to 20 CFM per pair. And so in the top right example there, we need 59 CFM of airflow. So we use 3 pairs to provide 60 CFM of airflow. The owners actually turned those down from 20 CFM to 15 CFM. So the reason being is because we put them in the bedroom. This is the first installation we did of these, and they're actually a little bit noisy at night at 20 CFM. So they turned them down to 15. So we learned a little bit of something there about these units here. So we can only count on them for 15 CFM. On the bottom right, we did 2 pairs there for his 1,200 square foot ADU that only needed 34.5 CFM. And there, so probably we should have done 3 pairs in that one there to do it at 15 CFM only. So there's a couple of examples of these systems here. They're great, inexpensive way to achieve balanced ventilation. Next slide, please. So the pros of a dedicated standalone ERV, they definitely provide the best indoor air quality of any of the systems that are available to you, whether it's supply, exhaust, or balanced ventilation. And so we exhaust air where we want to exhaust it. We bring fresh filtered air where we need it most. And as Kalina talked about, we can actually get down to MERV 13 in these systems. They're pretty much standard at MERV 8, but we can add additional filtration into these systems. They do provide excellent distribution of air throughout the structure because of the way that we're exhausting. So distribution is important. You're not better than just pumping air through the envelope. We are not really addressing distribution. Most of the leaky points are doors and windows when you're doing air that's makeup air through the building envelope, and it doesn't get really very good distribution. The problem with these systems is they can be expensive, but we say what is the value of healthy air, which really is one of the most important things we should be thinking about in our homes is our indoor air quality. People spend a lot of money on their countertops, and they think that ventilation systems are too expensive. But we think as a proportion of the total building cost, it's really pretty minimal given what you're actually getting at it out of the systems. The problem is they are a little bit complex to install, and it's hard to find local installers here. There's not a lot of call for them, but I think as we see the code changing, we'll see more and more of these systems and more installers understanding how to put these systems in. They do require adequate spaces to be for the equipment to be housed. So mechanical rooms do need to be significantly sized for them. And the low-cost pairs they still require bath fans and laundry fans. So that example we showed you, we still had to put bath and laundry fans in. And the problem is that was a pretty tight home that we built there. So we actually had to put makeup air systems in. So we're not bringing makeup air for bath fans, trying to suck it through the HRV systems. So that does add a little bit more cost when you put makeup air systems in. Next slide, please. Lastly, here's that home again. Just a couple weeks ago, I happened to be up there meeting with those folks. This is a picture of them. They just got back from a nice little trip to Sequoia. They sent me this here. So you can see they got just the two of them and their young daughter. They had thanked me saying that for forcing them to put in an HRV system because like a lot of people, they say, well, we live in San Diego. We keep our doors and windows open. Why do we need to put this expensive HRV system in? And we told them they really need it. They'll be happy that they did. And they thanked me saying that during our recent fires, they had to turn that off because it was bringing in smoky air from the outside. And they said a couple of hours later, they started noticing that their house started stinking and smelling bad. And it's not because of, this is a brand new home. It's not because of anything that we did in the construction. It just happened to be just living in your home creates stale air. So they hadn't realized how good their system was working until they turned it off. They said they couldn't wait to turn it back on again. So they really, really like their system. And I think that's pretty universal that people don't really know what really good quality air is until they've lived in a home with great quality air, and then that great quality air is not available anymore. So the humans are very adaptable. We can live in really crappy condition, but why would we do that? So we're firm believers in creating optimum indoor air quality for everybody in a home. It really, again, it should be the most important thing that people are thinking about in building their home is having good indoor air quality. Next slide, please. And that's it. See if there's any questions. I think there's one there. Oh boy, there's a lot of questions here. So which are the recent ones here?
Yeah, it looks like there's a question from Bob about a maintenance schedule in the code. And I don't know of one, but an operations manual that refers to all the equipment is required by Cal Green. So on a project, so in the operations manual for the equipment, there is a section on maintenance. Typically, it usually says every year and gives you some other instructions.
Yeah, and we are required to have provide a maintenance manual for the owners of the homes we build. And so that's included in their maintenance for the systems, but the code specifically, to my knowledge, does not provide any maintenance schedule per se.
And there's another question there, Rich, about attic wrap around the bathroom fan. Is that a requirement?
So that wrap, no, to me it's just the best practice, really, because you've got the choice, or the fan has the choice of pulling air through that grill or through that small gap between the housing of the bath fan and the attic. So why would you want to be pulling air out through your attic right there? So that's just something that I do. I like to do that. I don't think I've seen it elsewhere being done, but it's just one of those things that makes absolute sense to do. because it's never a perfect seal. There is actually quite a significant gap between the housing and the drywall there. So I see from Mark here, decision to upgrade from minimal exhaust ventilation to better systems being driven more by designers 24. Is the decision to upgrade from minimal exhaust ventilation to better systems being driven more by designers, Title 24 consultants, or the general contractors? Great question, Mark. General contractors are in general, with a few exceptions, I would say, like us, going to do the minimum they need to do. I was just in a Habitat for Humanity project where they didn't even know about the requirement for continuous ventilation, and they have single speed bath fans in there. I just found out yesterday in that same project, they didn't even put a bath fan into one of the bathrooms because whoever installed that still over 20 years behind in code and thought an operable window was sufficient to provide ventilation. So, but I do think that in the future, we are going to see Title 24 driving this. It's whether builders and even notice it, and it's going to be up to HERS raters and inspectors to let builders know that they have these issues they need to address in construction with new code upgrades with HRBs and ERBs. Great. I think that's it for my questions.
Thanks very much, Rich. We better keep moving along here. Of course, my phone rings right now. But next, we're pleased to have Joe Hadash with us. And Joe, you take it away.
Greetings, everybody. Hope everyone is well as they're listening to this. So I'm a healthy building scientist from Hayward Score. I have a little more information on Hayward Score on a few slides, but a healthy building scientist is someone who's actually concerns and focus on the chemicals and the materials we use in our buildings, as well as really good balanced ventilation. So when you combine that with building science, you end up with a healthy building. So that's one of my focuses today is what is a healthy building and how does it overlap with some of the energy conditions that everybody's talking about. Next slide. You heard a lot about new construction. You heard a lot about commercial. I'm going to focus on residential existing things. I think most people that are listening to this do live in a home. So I do have a fixed audience as no matter where you work, you probably go home to someplace. So this is a prop that I had made a couple of years ago for BPI CEO Larry Zarker. And the concept is that we think of infiltration as an energy penalty, but the reality is it's more of a health penalty or an IAQ penalty, that infiltration is actually an exposure pathway. And we really keep thinking of it as an energy penalty, but as I'll point out throughout this slide deck, there's multiple benefits that come along with doing these energy upgrades or infiltration improvements. Lawrence Berkeley Lab recently released something that says that our average walls that have fiberglass insulation could be equivalent to a MERV 8 or 13, but that's not really the place where you want to be breathing. In fact, I don't really believe there is a such thing as fresh air. It's just outside air. It may be fresh or it may be near a road or some other condition. So I refer to it as outside air. So our goal is to reduce that through a variety of opportunities that we'll have here. Next slide. So what are you breathing and how much? So I just wanted to take a quick slide to show on an average day, in general, we breathe in and out 3,000 gallons of air every day. That's a average size little swimming pool that you may have in your backyard of air every day. You could probably go hours and hours without eating or drinking, but you can only go a few minutes without breathing. And we don't really give as much importance of the air that we're breathing constantly, no matter where it is, indoors or outdoors. But I think that we're starting to make this more of a priority when we understand the significance and how much a day we actually are inhaling some of these conditions. Next slide. There was some mention in the commercial side about upgrading or using good filtration. Rich focused on some of the ventilation strategies. I want to go back to filtration because of all the things you could do in your home, this is one of the, I think, the most important and simple upgrades to do this. Again, it's only going to be operating when the unit is on, but when it is on, this is a great way to make sure it's using well, and you can actually have other sensors that can actually allow this to just kick on for 15 minutes, an hour, parts of the day. EPA's got some great guidance on how to use certain filters and how to make sure you're changing and upgrading your unit correctly. So next slide. What we're trying to do is, you can see on the left, this may look like the typical air handler and furnace or air conditioner setup you may have now. and that is that it's got a return on the left, and it goes down into a very small 1-inch filter. And you can see that the radius is really tight. Probably only the bottom of that filter is actually getting used. Meanwhile, for less than $1,000, usually around $600 or $700, you can do a great upgrade where you're actually moving the filter further up so that the entire flow is being caught by a good MERV 13 filter, and the pressure that actually is now moving through here is much lower, which means I have much better airflow. And if you do want to leave this on for a little bit of time during the day, it's not a major energy penalty. It's not making your motor run excessively when you have low pressure flow across that system. And by just moving the filter, widening that path, gives you a great solution. And I have some data to back up how these things are. So you're going to see in a minute here, data from the original and for the upgrade. Next slide. This is this source is from Linda Wigington of Raucous. They're out of Pittsburgh, where they actually have really challenging outdoor air, and they try to figure out a way to improve it. So you can see here on the before where their outdoor areas, their indoor, and the master bedroom. Right. And let's go to the next slide. You can see the upgrades where they did, you saw the filter upgrade, the better path. You could see green is good, red is bad, outdoor air is still bad, but because they got a much better drop on their system and added a better filter that's 4 inches, you can see the indoor air improved almost immediately just by doing this simple upgrade. So if you are looking for something to happen or do that, you can add charcoal to these filters for those times where you might have the fires outside. Next slide. So I have some data about Hayward Score. Hayward Score is a free online survey tool that anybody can take at any time. It takes about maybe 10 minutes or so. We're going to ask you questions about your house, your behaviors, and your symptoms, and give you a score and some recommendations on how you can improve that. Next slide. This is our basic conclusion, which is that the better score, clearly it gives us indication throughout our data that you have less symptoms. So if your home is well maintained and you're doing a variety of stuff on good filtration and good habits, then you're showing that we don't have on keep track of people performing have more symptoms, and I'll explain more about how that shows up in some of our data. Next slide. So we talked about ERVs and HRVs. So we did a study with some people we knew that actually had an ERV and HRV. We've actually doubled that number from 45 to about 100, but the actual scores did not change much. People that had ERVs and HRVs in their homes across America and Canada had really good scores. And that means that their homes were well maintained, a lot of good habits, a lot of good things that went along with that. But in general, they were getting great fresh air, and their infiltration rate goes down because the air in the home is balanced. Throughout our score, we asked people about that, but I can't confirm if you actually have an ERV or HRV. But almost 300 people said yes, they do, and their scores were again very high compared to those who did not have that type of installation in their home. So it's definitely something that is improving the symptoms that people are telling us about their homes. Next slide. We've learned a lot about asking people about the maintenance of your home, whether it is expertly or well maintained or kind of, or has some deferred maintenance. And these are some things, again, that are not part of the score, but are telling us about conditions that people are having. If you have a poorly maintained home, it means that your indoor air quality has been compromised from either connectivity through your crawl space or the attic or just outside. That the leakier the home is because sometimes it's not well maintained. So if you told me that you had a deferred maintenance or a home that wasn't well maintained, I could just assume by our data from almost 80,000 homes that you probably have some awkward odors in there. You probably have a lot of surface dust or sill dust near your windows. You either have water stains or even potentially visible mold, or think you have mold in the house, usually connecting back to the odors. So the better maintained your home is, the better your indoor air quality is, and the better the conditions are that you're living in. So just in general, this is a real good snapshot about the condition of our homes and how we actually impact our own indoor air quality by how well we maintain them. Next slide. Following that same concept, here's some of the conditions that people had, either asthmas or allergies or chemical sensitivities. These are all clinical diagnoses. And you can see the people who had well-maintained homes had less of these conditions showing up. And, asthma and allergies and chemical sensitivities are based on the conditions in your home. So if you're able to keep them well maintained, you can actually show that there's some improvement there. Next slide. We also talked about and document active symptoms, severe symptoms, or symptoms that are relieved when you leave the house. And again, it just kind of reiterates that having a well-maintained home is providing a healthy environment for you and your family. So it's something that is usually for a lot of us kind of forgotten about. Some people do analogy of cars, and we usually maintain our cars sometimes better than our home. So I'm just trying to remind you that these things do have a direct impact on you. So next slide. We did a follow-up survey for those who took our survey. Said, hey, what are you guys doing? Are you improving your home? Are you doing some of the things that we recommended for you? And in general, almost 60% made changes. Even renters made changes who are actually kind of limited on what they can do. 6% moved. Those were actually a lot of renters that actually had moved based upon the information that we provided back to them, that we felt this was not a healthy environment and they should be considered relocating. A few of them, we actually got lawyers involved to help them get out of the environment that was because it was so bad for their conditions. Next slide. So here's the things that people were doing. They were spending their own money on some of these things. More homeowners were doing some of the larger things, but you can see that 17% added an HRV or an ERV. Many people are cleaning their ducts, added humidifiers, dehumidifiers, exhaust fans, sealed the crawl space. All of these things are improving many of the indoor air quality conditions that we think of in the home, which are also improving how they felt about their home. So when you educate somebody and give them good information and simplify the upgrades that are out there, either they'll be doing some of this stuff themselves, like removing carpets or reducing their chemical use, or they're going to hire professionals to come in and help upgrade that. So all of these will many of these will reduce your energy load in general, but they're really going to make your home a much more better IAQ and a healthier in general. Next slide. Of that group that we just saw, these are some of the symptoms that they also told us had improved. So based upon those folks, that their sinus congestion, coughing, allergies all will reduce significantly based on some of those upgrades. And the non-respiratory feeling sick, sore throat, headaches, all those also were reduced. So there is a direct connection between the things that we're living in our home, doing in our home, or improving in our home can actually be something that is a health improvement. There's no guarantees about anything, but in general, if you follow best practices, you end up with typically following the percentages that could be here. Next slide. One of the things I want to try to work back into, I mentioned in the beginning, and that is that the things we're doing for energy improvements usually have a much larger health impact on the things we're doing. We talk about the energy code or some of the ventilation strategies in commercial building, but there's lots of good studies we couldn't spend time on today that are actually showing the amount of improvements from cognition and improvements from workers, feeling better in your home. All those things are coming from the energy improvements we're doing in our home. So you can see on the left, air sealing, upgrades, ventilation, cooking efficiency, all those things ended up showing that they had reduced hospital and medical visits, and some of their symptoms were relieved, and they're well documented in this study. This is the E for the Future study, and on the next slide shows this one and a few others combined. Next slide. Yeah, so here's one of the ones I try to, it's a lot of information here, kind of dense. I'm going to read it to you kind of quickly. So just by doing basic air sealing, thermal upgrades, adding insulation, which always goes along with air sealing, and heating tune-ups. You don't have to replace your system, but make sure it's tuned and working correctly. Whether or not you even do the conditions I talked about on improving the filtration, these are just some of the basic things to make sure your home is well maintained, or you improve some of these. So the conditions that were reduced were clearly gases and particulates, less medications were used, dampness, mold, risk of cancer, arthritis, depression, energy bills were reduced, and pollutants. All these are well documented throughout both of these studies that they had. Some of the other improvements were clearly they're saving money. They have more income to do other things with their family. General health, mental health, upper and lower respiratory, blood pressure, which are all connected to particulate conditions. All these things were documented improvements through a variety of studies, many of which were with state weatherization programs, but they did a great job of actually documenting the conditions that were there. in general, you have a better quality of life. And these are not just energy reductions, these are long-term health impacts that actually improve the lives of the occupants for not just this home, but the next home and other homes in general. Next slide. Many people are familiar with the blower door. The blower door is something that is a tool that's used usually for energy loss or infiltration, as I mentioned in the very beginning. But the reality is it also is an exposure pathway measurement device. It determines how connected my garage is, my attic or crawl space, or other areas that I really don't want to be part of my indoor air breathing area. So we think about these things as, again, an energy loss, but I'm trying to remind you that there is actually a connection between your home environment and other things that really go along with a healthy IAQ that you're actually breathing. That air leakage is heat transfer. It's also an exposure pathway transfer. Next slide. I want to give one reference here, and that is that this is a book you can purchase from Rob Dunn. He's got a couple, and this is not about creepy crawly things in your house like the image may imply. He's talking about they're using these types of things that are in the homes to determine whether or not your home is has still biodiversity. He's showing that there's lots of great studies that are showing that we're actually losing the biodiversity. We're not connected with outside. We're not able to maintain the type of healthy environment living that we should have. And now that COVID has hit, we're over cleaning, we're under ventilating, we're home a lot more, we're shedding skin cells and all kinds of stuff in our home that are all impacting our health, and we're losing our own potential to have a good biodiversity in your home. So if you're looking for a great book that outlines through great studies across the globe that have proved that we actually do need to do a better job of connecting ourselves to outside, which includes ventilation, includes opening windows, includes doing these kind of things, this is a great book that covers that. Next slide. The last one is that we are in a new realm, not just because of COVID, but we've been making homes tighter and tighter. And now there's actually various techniques that you can use to make homes super, super tight in a matter of hours and eliminate a lot of the challenges that go along with making homes tighter. And Verilux made one of the best videos out there that talks about the indoor generation. In fact, the college graduates that just struggled to graduate recently last year were the first ones who came through this indoor generation. They were the first generation to be indoors more than any other generation in general, from playing indoor games, not doing outdoor sports, just a variety of their lifestyle was probably that 90% of time spent indoors. Meanwhile, if you were probably 50 or older, you were probably outside more than this generation. So we're now beginning to see some of the impacts that's happening on these types of folks who have spent a lot of time in really what are not the most health conducive environments. So if you're looking for video, here's a link here, but you can just research or type in, indoor generation and find the video online. It's very eye-opening. Next slide. That's it for me. I had just a quick overview about what you can do to realize that your home it can be impacting your indoor air quality and your health. And know that the energy upgrades that you may want to do for your existing home usually have more health benefits than they probably do energy benefits. So anything you're doing in your home will be a great improvement for you and your family.
Okay, thanks, Joe. We went a little over today, so most of the people could stick around. That's great. And it is being recorded, so other people can catch up later. And there's this one question here from Bob Coleman. Do you see that, Joe?
I do. Are contractors that are replacing old attic routinely air sealing? I don't believe that many of them are. I think the concept is, more R value and more insulation is better, but the reality is for your money, the best bang for your buck is to air seal. Make sure your insulation is installed correctly. Even if you don't even add any more, air sealing will provide a better thermal boundary because the infiltration has now been eliminated, as well as the other benefits we talked about.
Okay, well, thanks to everyone that presented today, and thank you all for attending. And we will be sending out the presentations and information about the ICC CEUs if you attended live today. Okay, thanks very much. Have a great day.